Welcome, Calculus, to curve sketching, the final frontier of graphing. So everything that you've done in the last lesson where you were given all the properties of the graph, we have to find those ourselves. So this is still from section 4.6. Okay. So normally when I do this in class, I say, what are things that you think the graph should have on it? But we kind of did this already, so I'm just going to make a list of things that when I'm asking you to sketch a graph, things that we should know. So you can copy this down, but we should find out what the domain is. Vertical asymptotes. Horizontal asymptotes. X-intercepts. Y-intercepts. Where it's increasing or decreasing. Intervals of increasing / decreasing. We can use that to find relative extrema. The concavity. Points of inflection. And I said domain, so the range. So I'm going to give you a function. We're going to try to find out all this information about it so that we can sketch what it might look like. So in general, how do we find these things? So the domain, think if we're ever going to divide by 0, values where you're dividing by 0 are not going to be in the domain. Taking the square root of a negative number, that's not going to be in your domain. And not just any number, not just square rooting, but to the 4th root, to the 6th root, to the 8th root, so any even root. So I'm going to call it the 2nth root. This doesn't come up often, but the natural log. You can't take the natural log of anything 0 or less. So the natural log of 0, -1, -2, -3, and this is true for all logs. You'll get a D and E. So those are places where we that are not in our domain. Vertical intercepts. Excuse me. Vertical asymptote. That's when the denominator is 0. Think to the rational functions. There could be a hole if it divides out. Right. Think of like the limits. Think about like the limit as x approaches 5 of x plus 5, x minus 5 over x minus 5. If I plug in 5, I'll get a 0 over 0 situation here. But if they divide out, that would be there would just be a hole there. There would not be a vertical asymptote there. I'm just going to erase that though. All right, horizontal asymptotes. Just look at the degree of the numerator and denominator, which we'll call n, and denominator, which I'll call d. So if the degree on the top is bigger than the degree on the bottom, then no horizontal asymptote. There'd actually be something called a slant asymptote, but we're not going to deal with that for now. If the degree on the top is less than the degree on the bottom, then the horizontal asymptote is at y equals 0. And if the degree on the top and bottom are equal, then it's going to be the leading coefficient of, the ratio of the leading coefficients. Okay. So we had something like 4x squared minus x over 3x squared plus 1. The degree on the top and bottom are both 2. So the horizontal asymptote would be at y equals the ratio of the leading coefficients, which is 4 and 3. Anyways, so let's get rid of that. Here we go. Come on. All right, so to find x-intercepts, that's when you're just trying to find out what x values does your function equal 0. To find the y-intercept, you just plug in 0. See what the value of the function is. Increasing and decreasing, that's when we use the derivative. That's when we use the slope. Concavity, we use the slope of the slope, which is the second derivative. So we'll use that for concavity points of inflection. All right. So it's good to have graph paper out when we do this, but if you're going to do any notebooks, that's fine for now. Let's go and find everything. So let's find the x and y-intercept. So the y-intercept is going to be the easiest to find. We just want to find out what f of 0 is, which is going to be 0 cubed minus 4 times 0, which is 0. So 0, 0. To find the x-intercept, we want to find out when f of x equals 0. So when does x cubed minus 4x equal 0? Here I'd factor out an x, and I'd get x squared minus 4 equals 0. And that factors to x plus 2, x minus 2, because that's the difference of squares. So x equals 0, x equals negative 2, and x equals positive 2. So I already knew 0, 0 was an x-intercept, so I'm not going to write that one. But I have negative 2, 0, and 2, 0. So right off the bat, I got 3 points. 0, 0, negative 2, 0, and 0, 2. I did not mean to cross that out, though. Okay. So those are our intercepts. Let's do vertical asymptotes. So that's in the denominator 0. There's, I guess the denominator is 1. There's no way you're going to make that 0. It's not even a rational function. It's just a cubic. So there's none. Horizontal asymptote. Again, the degree on the bottom is 0. The degree on top is 3. So the degree on top is bigger. There is no horizontal asymptote. Again, it's a cubic. It's going to look something like this. So there's no asymptotes here. Where is it increasing or decreasing? That's when we need the derivative. So if I find the derivative, it's going to be 3x squared minus 4. To find the critical numbers, and we set the derivative, find out where the derivative doesn't exist or where it's 0. It's quadratic, so it's going to exist everywhere. So I'm just going to worry about where the slope is 0. Add 4 to both sides. Divide by 3. To find x, you just take the square root of that. It's going to be plus or minus that. Which for graphing purposes, it's about 1.15. We'll just say 1.2 because we're going to be graphing. Okay, so this is going to help me figure out if I have a max or min, that's where it's going to be. These are my crits. So if I make my sign chart with the derivative, we know that negative 1.2 and positive 1.2, or the slope is 0. If I want to find out what's happening over here, I'm going to plug in a number like negative 2 into the derivative. If you plug negative 2 into this, 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. I don't care that it's 8. I just care that's a positive number. If I plug a number between these two, I'm going to plug in 0. If I don't have it in the middle, if I plug 0 in, I just get negative 4, which is negative. So my function starts to decrease. And then if I plug in a number bigger than 1.2, like 2, the slope is going to be, it's still 2 squared is 4, but it's still going to be 8. Again, all I care is that it's positive. So my function's increasing and then decreasing, and then it decreases and increases. Again, it's a cubic, no surprises here. So we have a max or min. So we have a max at negative 1.2. And if I plug that into my function, I get 3.1. Check that yourself. Plug into the original function, though, not the derivative. If I want to find a min, that's going to be right here at positive 1.2. And if I plug it into my original function, I get negative 3.1. Again, you could plug those numbers in. to your original function. And I'm not going to write it down, but my function is increasing from negative infinity to negative 1.2 and 1.2 to infinity. And it's only decreasing between negative 1.2 and 1.2. When we graph, we're just going to have to remember that. And then for the second, or for the points of concavity and intervals, intervals of concavity, points of inflection, we need the second derivative. So the second derivative, I need to derive this, which is just going to be 6x, which is lovely. I want to find out where that thing is 0 does not exist. So it's going to exist everywhere because it's just a linear function, but it's 0 at 0. So if I look at my second derivative, I look at 0. We can have an inflection point here because 0 is defined in my original function. So let's look at the concavity if I'm less than 0, and what the concavity is if I'm greater than 0. If I'm less than 0, I plug in a negative number. 6 times negative 1 is negative 6, so it's negative, so it's concave down. If I plug in a positive number, 6 times 1 is 6, so I get a positive 6. So my function is concave down up until 0, and then once I get to 0, it switches from concave down to concave up, so we do have a point of inflection here. So point of inflection at when x is 0, plug 0 into my original function, and you get 0, which is also where the x and y intercept are, which is fine. So the last step is just to graph it, and with all this information that we have, we can do so. And it's a cubic, so we kind of have an idea what it's going to look like anyways. So 0, 0 is a point. And then I think we said 2, 0 and negative 2, 0 are also intercepts. At negative 1.2, so we have some more points here that I can plot. At negative 1.2, we have a height of 1, 2, 3, or just over 3. And at positive 1.2, we have a height of negative 3.1. 1, 2, 3, right around here. Okay. So this is a relative max. This is a relative min. We know that. We have a point of inflection here. And so my function I know is increasing up until I get to 1.2, and it's concave down. So it's going to be concave down, but increasing. So it's going to look like this. Then we have a max here. Now the function is going to start to decrease, so it's going to go down, but it's going to stay concave down up until I get to 0. So stay concave down up until I get to 0. Then we have a point of inflection. So my concavity is going to switch from concave down to concave up, but it's still decreasing. So concave up is still decreasing until I get to 1.2. Then my function will start to increase, but stay concave up. So it kind of looks like you would expect, a nice cubic function. No surprises there. But we didn't need Desmos at all. We found all the information via algebra and calculus. So that is the first example. You can copy this down, and we'll do this last one. And then in class, we'll get time to practice. So first thing, let's find the intercepts. So let's find the x-intercept. That's when f of x equals 0. And in this thing's a fraction, so I really just need to find out when the numerator is 0. So that's when 2x squared minus 18 equals 0. So that's when 2x squared equals 18. Divide both sides by 2, I get x squared equals 9. So I get x equals plus or minus 3. So 3, 0, and negative 3, 0. To find the y-intercept, just let's find out what f of 0 is. If I plug 0 into this, I just get negative 18 over negative 4, which is 9 over 2. So 0, half of 9 is 4.5. We're going to use decimals just because we're graphing points and it's going to be easier. So I know I'm going fast, and if you need me to if you want to rewind the video, that's fine. If you have questions about me doing things quick, just let me know in class. But right now I got my x and y intercepts. And now let's talk about asymptotes here. So I have a vertical asymptote. That's when the denominator equals 0. So that's when x squared minus 4 equals 0. So that's when x squared equals 4, which is at plus or minus 2. So there's two vertical intercepts, vertical asymptotes. The horizontal asymptote, let's look at the degree on the top and bottom. The degree on the top and bottom are equal. So there's a horizontal asymptote at y equals the ratio of the leading coefficients, 2 and 1. 2 over 1 is just 2. Okay. So we have our asymptotes there. And now we want to find out where the function is increasing and decreasing. So we need the derivative. So there's going to be a good amount of algebra here. Low d high minus high d low over low squared or low low. So yeah, let's just do it out. Do the distributive property here. That's going to be 4x cubed minus 16x. So we have a negative 2x I'm going to distribute. So negative 2x gets distributed in here. And so I don't know how to draw this and make it look better, but this is going to get distributed in, but this 2x is really a negative 2x. So that's going to give me a minus 4x cubed, and it's going to give me a positive because it's double negative. 18 times 2 is 36. So 36x. All over this thing squared. These things kill each other, which is kind of nice. 36 minus 16 is 20. And I got x squared minus 4 squared on the bottom. So that's not too bad. So make my sign chart. So I want to find out, actually before I do that, let's find out where the derivative is 0 and doesn't exist. I mean, you could probably do it in your head, but so the derivative equals 0 when the numerator equals 0. So when does 20x equal 0? Well, that's when x equals 0. The second derivative, not the second derivative, the first derivative doesn't exist when you divide by 0. So that's when x squared minus 4 squared equals 0, which is when x squared minus 4 equals 0, which is when x squared equals 4, which is when x equals plus or minus 2. So this is a critical number. This is actually not a critical number. We already know that these are asymptotes. Not crits, they're asymptotes. Right, because if I plug plus or minus 2 into my original function, I get a DNE. You can't plug 2 or negative 2 into this because you're going to divide by 0. So just good to know. So 0 is my only possible max or min. I'm going to look at negative 2 and 2 to see if there's sign changes, but it's not going to matter because I know there's asymptotes, so there's definitely not going to be max or mins there. So we got to look at numbers less than negative 2. So if I plug in a number like negative 3 into my derivative, you guys can do it. But the denominator is always going to be positive because it's something squared. And the top, if I plug in a negative, I'm going to get a negative. So a negative is positive, it's going to be a negative. If I plug in a number like negative 1, the top's going to be negative because 20 times negative 1 is negative. The bottom's always going to be positive because it's squared at the end. Negative divided by positive is negative. Plug in a number between 0 and 1, like assuming between 0 and 2, like 1. So if I plug a positive number in here, 20 times a positive number is positive. Anything on the bottom, again, is going to be positive. So positive is positive. And if I plug in a number bigger than 2, like 3, same thing. The top would be a positive number. The bottom's always going to be a positive number, so I'm going to get positive. So I do have a sign change at 0, which is a critical number, so I am going to have a minimum there. So we have a relative min at x equals 0, and we already plugged 0 in, 0, 4.5. So that y-intercept's also going to be a min. And then we need to find out the concavity, so we look at the second derivative. So I take the second derivative of this, so again, low d high minus high d low. The derivative of that is going to be the chain rule, so it's going to be 2 times x squared minus 4 to the first, and the derivative of x squared minus 4 is 2x. So low d high minus high d low, all over low low, so x squared minus 4 squared now. So super simplification, they both have an x squared minus 4. I'm going to factor that out. I'm going to leave the 20 in because I feel like it. I'm going to take the 20 out. It'll make the multiplying stuff a little bit easier. So if I take that out, if I take a 20 factor out and x squared minus 4 factor out, there's still one x squared minus 4 factor left. This 20 is gone, but I have a x times 2 and a 2 times x, so that's 2x times 2x is 4x squared. So a minus 4x squared, right? Because this 20 is gone, x times 2 and 2x, and then x squared minus 4 to the first is gone. We factor that out. All over x squared minus 4, squared squares right to the fourth. Nicely enough, this x squared minus 4 is going to take out one of those ones, so there's going to be 3 left over. So we have 20 times, let's see, x squared minus 4x squared is minus 3x squared all over x squared minus 4 to the third. And we want to find out where this thing is 0, does not exist. Again, the second derivative is not going to exist at our asymptotes. So at x equals plus or minus 2, but not going to be points of inflection. Because we know that at 2 and negative 2 we have an asymptote. So we want to find out when this thing is equal to 0. So that's when the numerator equals 0. So I really just need this thing. The 20 is not going to, I just need the 3x squared minus 4 equals 0. Multiplying 0 by 20 would still get me 0, so that's fine. So then add the 3x squared to both. Yeah, it's not going to matter. If I add the 3x squared to both sides, I get negative 4 equals 3x squared. Divide both sides by 3, I get negative 4 thirds equals x squared. And you're going to get plus or minus square root of negative 4 thirds, which has no solution. Okay, no big deal. So that means so no points of inflection, which is fine. So then we just want to graph this all and be done. So here's my graph. I don't want that to be red. All right, we have 3, 0 and negative 3, 0 as our intercepts. 0, 4.5 as our y-intercept. At 2 and negative 2, we have asymptotes, so vertical asymptotes. We said we have a horizontal asymptote at y equals 2, so once we get to big numbers, we're going to approach this value of 2. And let's see, I have a minimum. So this is a minimum, so this is going to look like that. And my function is going to be decreasing up into it and increasing after it. So it's going to be decreasing to like as that asymptote would imply, and then starts increasing after that. So that makes sense. Right here, my function is going to be decreasing before that as well. So to have this asymptote and be decreasing, and my second derivative, I didn't look at the points of concavity. Shoot. So there's no points of inflection, but I didn't make my sign chart. So I know at negative 2 and 2, I have my asymptotes. If I plug in a number less than negative 2, I got a negative number. If I plug in a number between those two, I get a positive number. If I plug in a number bigger than 2, I get a negative number. Okay, so it should be concave down up until 2, and the derivative says it's decreasing, and we have all these asymptotes here, so it's got to be decreasing, be concave down, go through our x-intercept, and then hit our asymptotes. Now, once I pass 2, what happens? Well, my function is going to be increasing, but it's also going to be concave down. So it's going to be increasing and concave down. So it's increasing, concave down, goes through my x-intercept, and it hits my asymptotes. So that is what that function looks like. And again, it's a lot of work. It's putting everything together, but you do a couple of reps, you get a little bit better at it. And, I can't ask you more than 1 or 2 of these on a quiz because that would be like takes like an hour to do that. Anyways, have a good day. Like, share, subscribe, ring the bell for notifications. Comment if you like what you see.